Let's try to do a very simple structural equation model together. Now, as with all SEM, you need to start with a theoretical model. In our case, you can see on the slide on the right-hand side that we have the diagram depicting the model. So, what would you say this diagram means? That's right, we're simply looking at the relationship between mindfulness and happiness. Mindfulness is conceptualized as a factor, as a latent variable, comprising 4 items, which are very creatively labeled item 1, 2, 3, and 4. Happiness is a single, directly observed indicator. You can see that from the fact that mindfulness appears in an ellipse, whereas happiness appears in just a rectangle. So far, so easy. So let's see what the input file looks like. Here on the left-hand side we have the input file. And of course, as a quick summary, I have linked the data. You see I have used a different way of writing out the input instructions just so that you can get a bit more exposure. Now underneath we have the names of the variables as they appear in the dataset. And here, what do you think this means? That's right, it means that if I had any missing data on any of my variables, that would have been coded with a -999. Underneath, I have listed the variables that I was going to use in my model, specifically all of them. By the way, note that here we don't have an ID variable. So for an M+ model, you don't necessarily need to have an ID variable, but I strongly recommend you have one in all of your datasets. What do you think this means? Why have I used the robust maximum likelihood estimator? That's right, it's because my dependent variables are all continuous. That's what that means. If they weren't, I should have put another command somewhere here in the variable section stating that they are of a different kind, for example categorical or count. So first of all, this means they are all continuous, and second, it means that at least some of them are skewed. Why do you think I mentioned that all of these would be dependent variables? That's right, if you look at the slide here, you see that happiness is obviously a dependent variable in this regression path here. But the items are also considered dependent variables because this is the factor analysis framework. So let's have a go and try to write the model out. And while you try to do that on your own, I'm going to fix this bit here because it's not quite right. I mean, it's not wrong, it's just that I prefer everything to be the way it should be. So have a go and try to write out the syntax for this model in the model section here. Right, so let's have a look at this slide again. What kind of statement would this one here be? By, on, or with? That's right, it's a by statement. In fact, all of these are by statements. They are used to define the factor by the items. What about this other one here? What kind of statement is this one? That's right, this is a regression path, so this would be an on statement. So when we want to write the input file, the way it would go is this. We have to give our factor a name, so I'll just call it mind. So this would go mind by item 1, item 2, item 3, item 4. And then for the regression path we would say happy on mind. And that's it. That's the model. Super easy. So let's run the model and check the results. Now let's scroll down to the model fit. In your models, I recommend you always look through all of this stuff. Don't take them for granted because you never know what kinds of warnings you will get here. And also it's good to check little things like, the number of observations is the one you expect it to be, or that there's only one group, etc. But in our case, let's go straight down to model fit. What do you think of this model fit? Good, bad? Would we publish it or not? Right, so the chi-square is significant and quite large, which is not great, but we can always ignore that, especially because we had a really big sample, 18,000 cases. The RMSEA is not below 0.06, but it is at least below 0.08, and even its upper bound value is below 0.08 if you were to, specify it to only 2 decimal places. So perhaps the RMSEA is okay-ish. The CFI only barely makes the lower threshold of 0.90, but we would actually ideally like it to be at least 0.95. The TLI, on the other hand, is actually pretty bad. It should also be at least above 0.90. And the SRMR is below 0.08, which is okay. So the model fit is not that bad, but this is actually a grave concern. Now, I was mentioning before that when you have a good CFI and a bad TLI, it could be the case that something is not significant and you could take it out. That's because of the penalty function that the TLI has in regard to redundant paths. The TLI and the RMSEA both favor models that are more parsimonious. So let's scroll down to see if perhaps something is not significant. Have a look here. What do you think? Now, I suspect the first thing you will notice is that the loadings are negative. That in itself is not a problem at all, so long as you know for sure that they are reverse coded relative to the first item. However, in general, I do suggest that you code your items such that they all point in the same direction. That's because it's easier to interpret them and people do prefer those loadings to be positive. So what I usually do is I recode my items so that they all have the same valence, and then if I do get negative loadings, I check and recheck to make sure that everything is in order. In any case, they are all significant, except of course for the first item, which was fixed to be 1 in order to provide the metric for the latent variable. Underneath you have the regression coefficient, and you see that it is negative and significant. So, all in all, we can't really take anything out because everything is either significant or fixed. Well, what else could we do? I suppose we could try to see if we can add something in, and perhaps the modification indices will finally provide something useful. So let's keep scrolling down all the way to the modification indices. So here we are. We finally have some suggestions for modifications. Now the first column tells you what it is MPlus suggests that you do. What do you think those statements there represent? That's right, they represent residual correlations between the items. Some people refer to these residual correlations as correlated uniquenesses, and in fact I rather prefer that term, because I was mentioning in a previous video that in fact we are the ones who call those residuals. They're not necessarily residuals, and those unique variances could actually be a function of some other latent factor, or some other predictors, or something that's just not included in our study, so they don't necessarily have to represent noise. For example, 2 items could have a residual correlation or correlated uniqueness or correlated unique variances because maybe they have the same phrasing, or they might refer to the same kind of thing. So it doesn't necessarily have to refer to noise. Right, so in sum, all of the suggestions refer to residual correlations. The next column, labeled MI, is the actual modification index. It tells us by how many points the chi-square would improve, which is to say would become smaller, if we were to include those paths. The EPC columns, well, that stands for expected parameter change. So that is roughly the value that we would expect that coefficient to have if we were to include that path in our model. And it comes in two flavors, unstandardized and two versions of standardized results. Now, the general rule with this is that you should always only include one path at a time. Because remember, every time you rerun a model, MPlus has no recollection of what it did before. It simply re-estimates the new model, which is the modified model. So it just estimates everything together from scratch. So every time you add a path or remove a path or otherwise modify the model, this is just a new model and everything else could change. The second rule is that you should usually try to include the path with the biggest modification index first. So the driving bit is not the expected parameter value, but the modification index value. The third rule is that whenever you include something, it should make sense. And particularly for residual correlations that are part of a factor, people very much dislike it when you randomly include residual correlations just to improve model fit, because you are capitalizing on chance. And your model might look better, but now it will be very much data-driven, so it might not mean much in the real world. So if, for example, you see that correlation between item 4 and item 1, which provides the biggest MI, well, hopefully it also makes sense from a theoretical point of view, and perhaps those two items are supposed to be correlated. And finally, the fourth rule is that practically you're not supposed to modify the factor after you've included the regression path. And this is the major point. When you do SEM, you should first build your measurement model. Because what's the point of connecting variables if you haven't yet defined them and gotten a sense of what they actually are? So you should always first do your factor analysis before you include any other paths. Now, SEM is comprised of a measurement model and a structural model. So in our case here, this is the measurement model. And this is the structural model. So we really should have just done the factor first, found a factor structure that fits the data, and then added on the structural paths. So let's do just that. I'm going to go back to the input file and work only on my measurement model first, which is what I should have done to begin with. Right, so we are back at the input file, and I'm going to do what I would suggest you always do first. So I don't recommend that you first have a look at the big structure and then go back and refine it. I recommend you start the way I should have started and just do your measurement model first. So now this is my measurement model. I took out this variable from the use variables section and I took out the regression path. Let's click run and see what that model looks like. Okay, so scrolling down to the model fit, what do you think? Good or bad? That's right, it's pretty bad. RMSEA is bad, TLI is bad, CFI is kind of okay-ish, and SRMR is good. But this just isn't quite good enough. I think we can do better. Having a look at the factor loadings, well, they are still all significant. So let's look at the modification indices now. So which path do you think we should put in? It looks like these two here are really vying for first place, but let's go for the correlation between item 1 and item 4. So I'm just going to mark it out here on my diagram. So let's go back and put it in the input file. Now the way I usually do this is I copy-paste this statement, the whole statement. I just copy it here by clicking Ctrl+C. And then in the input file, I paste it there and put a little semicolon and exclamation mark, because this allows me to remember what the MI was when I included that path. So let's run this model. Right, so let's check the model fit now. What do you think? Right, so it looks scarily good. It looks almost like that thing that we see when we have no degrees of freedom, where everything is perfect. So when I see something like this, I immediately look at my number of degrees of freedom, which you should always look at anyway. And I notice I still have one left, phew. But also the chi-square value is very close to 0 but not quite 0, and its p-value is, well, very close to 1 but not quite 1. So you know that in this case, all of these values that you see down here are true values. Let's have a quick look at the loadings. They are still all significant, and on top of that we also have that residual correlation, which is significant. And let's have a quick look at the modification indices. So you see they have now all disappeared. There are no more modification indices. So now we finally have our measurement model. Let's go add in the structural model. So now it's time to add in the regression path. And that's it. Let's click Run and see what the final model looks like. So scrolling down to the model fit, what do you think now? Indeed, it has excellent fit. All the fit indices are very good. Scrolling down to the model results, well, why don't you have a go at trying to interpret everything you see here? Excellent. So first of all, you see that all of the loadings are significant. The regression path is also significant and negative, whatever that might mean. And the residual correlation is also significant. Now what might have happened is, it is possible that the first item is the only one in the scale for which higher scores represent lower mindfulness. That would explain why the other items have a flipped loading, and why we would get this bizarre regression which is negative. So this is something you should have checked in your dataset to make sure that everything is the way you want it to be. And this is again why I recommend you recode your items so that they all have the same valence and they all point in the same direction. So here we have the variance of mindfulness, and from the fact that it is significant, we can deduce that our respondents had varying levels of mindfulness. They were not homogeneous in their level of mindfulness. And finally we have residual variances, which represent the leftover variances. So for the items you would say that those are the unique variances of each item, and for the variable happiness we would usually verbalize it as the amount of variance in happiness that was left unexplained by the predictor. And this is our full SEM. Well done!